Welcome, everybody. I know today you won't be able to see me, but we have a bit of a different setup today. But thank you so much for joining us today. And my name is Jessica Rodriguez, and I'm the Industry Engagement and Outreach Officer for the Data Science Institute here at Columbia University. Today's seminar is an iCubed, which stands for Institute, Industry, and Innovation. These seminars connect our industry affiliates to our students and to the larger Columbia community to explore topics at the forefront of industry. We invite data scientists, engineers, and researchers from our affiliate partners to give a talk about a recent project, case study, or the data science work that they're engaged in. During these educational events, we encourage attendees to ask questions via the chat and Q&A feature, and if you're in person, at the end we'll have a Q&A session. Today we have Dr. Paul Ardis, Machine Learning Technology Manager from GE Research. Dr. Ardis received his BS in Computer Science and Mathematics from Purdue University and his MS and PhD in Computer Science from the University of Rochester. Prior to his work at GE, Dr. Ardis is posted as a DoD Support Research Associate Professor at Rochester Institute of Technology and a consulting research scientist under contract to the Air Force Research Laboratory. Today's talk is titled, The Future of GE Innovation. A bit about the talk. On September 13th, GE announced the formation of 3 new advanced research centers in upstate New York, supporting GE Healthcare, GE Aerospace, and GE Vernova. This marks a refinement and focusing of the vision for innovation originally set out by Thomas Edison. During this iCubed talk, Dr. Ardis will go into detail about some of the research horizons each of these arcs will be pursuing. Thank you for joining us today, Paul.
Thank you very much, Jessica. And thank you, everybody, for coming and for attending remotely as well. So, to jump right into it, basically, we're starting from GE Research, and we're looking at the future going forward. So we're at a situation where GE itself has an intent to go from something that started in literally a backyard, so this would be one of the backyards in, actually, I think it wasn't Thomas Edison's his own, but it was Steinmetz, his buddy, his backyard in Schenectady, where they actually started a bunch of their experimentation, to this, which is the current research campus that we have in upstate. So what we're looking at is we need to continuously change. We need to look forward to what's going to be happening for the company and what it means from a research perspective. And for this talk specifically, I'll talk about what that really means from a digital perspective in terms of the technologies we're looking at, the frontiers we're hoping to pursue, and ultimately the change we want to have. So GE is splitting up. GE will be creating 3 separate companies: healthcare, Vernova, and Aerospace, focused on healthcare, power generation and decarbonization, and aerospace. But the basic timeline for that is that we've got the healthcare spin that happens basically right at the start of the new year. And from there, we need to already be making sure that we have research that is aligned with it. For the other 2, as we have a focusing on both our power generation and our aerospace in divergent directions, we need to make sure that the research that we're doing is ready. So what it comes down to, as somebody who currently works upstate at the research center, is we need to be ready to do all of this and grow in all 3 directions at the same time. So it's a very, very busy time at GE Research. So what it starts from is the actual research center concept itself. Right now we have a singular GE Research located in upstate. It's in Niskayuna, New York, just outside of Schenectady, Capital District area. And we're going to now have 3 co-located research centers on that campus, as well as having presence in Bangalore and elsewhere. So the main thing with having those co-located research centers is that we're actually going to have dedicated space, dedicated investments by each of these different nascent companies in that location, with the intent that they can collaborate together still going forward. So the thought is that we should still be able to work together to some degree, and we're going to be fostering it from where we actually started the research center journey in the first place. So for the rough size and kind of division of things as they look today, This gives you a sense for just sort of a breakdown from the current staffing in terms of the little over 1,000 full-time researchers that we have now, and how we have an intended initial alignment across these three different ARCs, or Advanced Research Centers. Down below is sort of a distributional take on the different technical disciplines and how they kind of interplay with these. So as you might imagine, for instance, our healthcare Advanced Research Center has a lot of biology and physics researchers who are currently in GE Research, who will now be GE Healthcare Research employees. Likewise, our aerospace business has a lot of folks who are in materials and mechanics. Now, I'm in digital research, and we do digital research for everything. So as you can imagine, the actual, the core foundational digital research team that we have now is actually going to be supporting all of these missions and has to grow very rapidly to support the fact that we have massive need under all three of these. So, talk about what exactly that means. But for the sense of how this comes to be, we're sorting out essentially who's going to be going where at the present in terms of determining the initial alignment. And as we have this and the transition and the shift to the new business system, we will also be continuously growing each of these. And so the sense is that we'll have 3 advanced research centers ready to run, ideally from day 1 for each of the businesses. So, big point of the talk, the reason why I wanted to give you guys some information about this really is about what we're doing. So we have a few different things, and I'll go step by step through the different advanced research centers and 3 of the main focus areas for each. And as I touch on them, I'm going to try and hit it so that you have a sense for some of the actual tech that we're applying there, the connection between the things that you're learning in class or that you might be trying out as an internship, and back into what it actually means in the real world for our customer base and ultimately everybody we serve. So starting from aerospace. First things first is that aerospace is looking to advance the future of flight. So this here is an open rotor design. It looks old-fashioned, if you will, in that it is moving away from a completely contained nacelle-based arrangement for improved efficiency of the system itself. And in fact, specifically, improved efficiency as it's tied in with a hybrid electric system. This is one of the first hybrid electric engines that are going to be out there flying basically every plane you see. And the intent is that we have, and we're going to be moving from the traditional aviation world to one which is going to have a reduced carbon footprint, the ability to have long-term sustainability from everything in the fueling, the potential even to fuel completely with hydrogen as a possibility, sourced through renewable generation, but then also to have things which are much more intelligent about how they're operating for potential self-repair. So, and to that last point, there's always been activity to try and understand the current health. We've always been doing something to try and understand when something is going to need to be fixed, because that means that planes are not grounded, that means that they're able to fly, it means people get from point A to point B, which is our mission. But a big part of planning and systems today currently attempt to do their understanding without having a good sort of intelligent and safe way to fail. So when they hit something and they hit evidence that counteracts what they currently have as a best approximation of a system, they look for the next best training from scratch. There isn't this intent to have a system that will naturally fall from one plausible hypothesis to the next most likely hypothesis and have a system that does not then force itself to rapidly reconfigure. Now, if you think about just the diagnostic piece of this, generally it's okay if you wanted to completely change your mind. But when you think about actually operating supply chains based on this, that suddenly becomes a very big deal. And so the idea of having systems where, for instance, in a dynamic Bayes net approach, you're not just looking for your dynamic Bayes net update to say, find the next best network arrangement for this, but you want to explicitly penalize it to some degree based upon massive reconstruction. So if you have any situation where you are going to be expecting that consequences of it may be supply chain dire, you want to be taking that into account. So that's actually something that we're digging into a lot in terms of research. How do you thread the needle from all the way from initial diagnosis to timing of when we do the inspection of the systems accordingly, expectation for what they're going to be seen at the shop itself, and then the resulting inventory that you're scheduling well in advance. So aerospace has space in the name, and the next part of it is looking beyond that. So we want to look beyond the fact that we are just flying around in the sky, but actually going to be sending things into space. GE has, for quite some time, been looking at advanced materials to support missions like this, partnering with NASA and others. Right now, the biggest thing that we need to do here is we need to have systems that are going to be much, much, much more autonomous. So it's great to talk about autonomy in concept. It's great to look at different things that can operate on the ground. What if you need something that has to be able to reason where you know that there's a fundamental lag in potential correction, just given distance into outer space? So we have a lot of activity based around curriculum learning and how you can do learning from human subject expertise in a highly constrained environment. So very few number of interactions, but that you are desiring to tune each and every interaction that you're going to have to maximize that information gain. So a lot of what we're looking at right now for that is all about how can you do intelligent system learning and specifically try and force an exploration of a variety of different consequences to sort of what if all of these things that could potentially go wrong. Obviously, you can't do this in a truly exhaustive fashion, so it's all about how do you quantify and effectively make use of steerability in some reduced latent space. So GANs, imitation learning, comes in very heavily. Everything from theory into practice for this is something that we're doing a lot of today. And then looking for the national defense side of our mission as well. GE is continuing to produce things that it believes can help bring peace to the world by providing a disincentive for armed combat in the future, and specifically to ensure that we have minimal need for needless loss due to critical failures of critical systems. So you don't want helicopters flying out of the sky and things like that. So design for sustainment, design for the fact that we can have safety guarantees built into their function is a big part of what we're looking at. And that actually ties into something that is both commercial and military side for us, which is all about test watchdogs. So when you go and you test a new engine or a new system, the goal, of course, is that you're going to have this very complex test campaign. And you want to be able to do that without actually destroying the thing that you're testing. So it's non-destructive testing, but you are necessarily putting it through paces that you may have never seen data like this ever before, or in extremely, extremely limited cases, maybe years previous with semi-related architectures. So the thought is, how do you have a system which can do anomaly detection in that setting without basically flagging all the time? And that's a huge challenge. So what we attempt to do is we create systems that do causal modeling that is learned on the fly. So basically trying to say, I am going to try and learn as rapidly as possible the causal connections of the system itself in terms of, a temperature goes up and the pressure goes down, one before the other, and that's something that we naturally expect. And that you can try and then match those up against physics-based expectations for the same system, and use that in order to execute the test in a safe fashion going forward. So we've been running this already, looking at a number of different architectures for commercial engines, as well as a few on the military side. The big thing is then, okay, well, you also want to be able to transfer learn from everything you have ever seen before, which becomes large models, large engine models, just like large language models are very popular, or they're used in terms of things like DALL-E for art. So it's an interesting world to play in, but it all comes down to trying to learn those dynamics and then trying to make sure that they have some sense to them, so that we can match them up with human subject. So switching gears a little bit, from the aerospace world to Vernova, the mission for Vernova is sustainability of how we have energy throughout the entire country and the world. So we've been working on the renewable generation problem for years, and we have a whole bunch on that. But more and more, it's now looking at not just can we continue to put more turbines out into the world, can we make them cheaper, but more, can we run them more effectively? Can we make sure, can we rely on them in ways that we can really turn off traditional baseload power and rely fundamentally on renewables in a way that we really don't as a society? So there are a couple big challenges there. First one, of course, is the shift from onshore to offshore. So onshore wind has reached a reasonable level of maturity throughout the world. Offshore wind is definitely still in its infancy within the United States. Getting there in terms of Europe, but when we think about, whether or not you see wind turbines up and down the Hudson or off the coast here, we're not there yet, but we will be. So the question is, how do we get that to work? The biggest problem is just that if anything goes wrong, it's incredibly expensive and frustrating to deal with. And because it is so inaccessible, the concept of minimal climbs and robotic climbs for dealing with the system has to be at the core of what we even architecture put out. We can't just assume nothing will break. We have to plan for what we do and how do we respond as when things do. And that actually then ties into materials and coatings for that too. So a lot of it is how do you restore the systems in place more than totally swap them out. Because if you had to take down an entire turbine blade and ship it up the Hudson, that's suddenly much more disruptive and expensive than being able to do something to repair, say, a lightning strike or a crack that has occurred to that. And then the other part is, as you get more and more of these, the biggest thing is that they interfere. So one turbine causes there to be a wake effect behind it, and then you have another turbine which gets hit by that wake effect. And that can be good or bad, depending on the setup. But we have to try and understand and be able to model this effectively. Because at the end of the day, our goal is that we want to have absolute continuous expectation of power generation in any condition if possible, certainly as best as possible, but we can't rely on some centralized, perfect scheduling system to just kind of figure this out, because we can't predict the weather. Not reliably, not at the density that we need for this. And so we need to have adaptive systems that can learn locally and communicate in order to coordinate and deal with wakes and other effects. And a big part of that comes down to how do you understand what's going on and express it in a highly compressed fashion. So for when something does go wrong, we want to run it down, but also just for when we want to pass information from one turbine to another. A lot of the concern there is in how do you do an efficient encoding. So you can try and learn a reasonable encoding of multivariate time series with something like time series sketching, which basically says you're going to provide a representation by which you can then reconstruct what happened. But at the end of the day, it doesn't matter if you tell the next turbine over exactly what you're seeing. What you want to tell it is what it needs to do about it. And so you actually want to have your learning system have that solution-based loss be part of it itself. So it's looking to tie in additional features of your loss function, which are built not on reconstruction itself, but are all based upon expectation over what the response is going to be and what effectively the penalty of them taking the wrong consequential action might look like. So if you tell somebody, hey, I'm braking, and they see that you're braking, that's great, but if they see that you're braking and do nothing about it, then it doesn't matter you told them. And that's all what we're trying to get around. Next thing up is all about then the connection in with the grid. So we have tons of distributed energy resources, or DERs, like wind turbines, like solar panels on roofs. And the biggest thing there is we want to be able to constantly use those as best as possible in order to shut off more and more of traditional base loads. Because even though, we could keep selling coal-fired power plants, that's a terrible way to live. And so the goal is that we want to be able to have intelligent monitoring of all of that the ability to marshal them dynamically and to have local storage or local consumption of other factors, so whether that be hydrogen production, actually distributed compute, so think running a co-located data center by major renewable generation, or other factors like that. Can we do that in an efficient and intelligent manner that we can also then keep tabs for it, so when things break, we can try and repair and restore as best as possible? So that's the other thing. Part of our mission here is we expect that things like hurricanes are going to continue to happen, and if anything, are just going to get worse for at least the next decade. And so what we need to be able to do is have systems that can handle that effectively. And that actually then ties into our concept for how we control networks. So we have transmission and distribution networks, which are trying to get power from point A to point B as best as possible to ensure that everybody who wants to keep the lights on can, all of the needs are currently met, all of the future needs are met as best as possible. We can have a dynamic system for doing that, but there are issues like we need it to be able to reason in a truly distributed fashion for security purposes, so that somebody can't just say, hack the entire thing and take it all down. But also we need to have a means for having the ability to do some learning from past experience for when these do fail in order to fail gracefully. Again, the biggest thing is that if you just train a reinforcement learning system naively on this, it can learn really efficiently to run that network and then do terribly at recovering for when that network changes, or when a single node goes offline, or a single piece of its expectations. So a lot of it is how do we figure out how we can use human domain knowledge and embedded expertise in that system itself for reward shaping. So we're currently working on a number of different ways to pull that off. It's getting there. And then that ties into one more thing that we're doing for Vernova, which is ultimately at the end of the day for all of this, the goal is to cut carbon production as much as possible and also enable the use of renewable energy for direct decarbonization activities too. So everything from direct air carbon capture to ocean-based carbon capture, we want to have a means for saying that we can pull all of the sort of the past generated carbon in the atmosphere out as much as possible, make sure that current systems are not doing it bad. So we've got different ways that we're trying to make sure that new systems that go out there, from modular nuclear on through to hydrogen burning plants, that they are not actually making it a lot worse. But the question is, how do we find the things that do actually efficiently pull enough carbon out in a way that we can say that that's something that we can rely on? And so to that end, a big part of that comes down to how do we dig into and find the next set of potential molecules that we should be exploring? We can kind of try and pick and choose various materials that we think are going to do a good job for it, but the ability to hypothesize new molecules that share properties that we have seen have proven empirically, but still can span a wide variety of potential options, that becomes a major part of our mission. Because however we can speed up the experimentation process for materials for this, the faster we can get to good materials for pulling CO2 out of the air, the faster we can get to actually making the world better. And so to change gears one more time, I'll talk a bit about some of the mission for healthcare and some of the different tech that we're looking at there too. So on the healthcare side, GE has historically done tons on the diagnostics side of things. So imaging has kind of been synonymous with a lot of the GE technologies, so MRIs and CTs. But there are a few things that need to significantly change in that world. So first things first is the ability to have radioisotopes available at hospital without basically having to ship them from a centralized location. So just like the idea of distributed generation of energy, distributed generation of radioisotopes for the use in medical imaging is a critical thing that we need to have happen. So that means we need low-weight cyclotrons. So we have, right now, we're able to put out basically a 20-ton cyclotron and drop it into hospitals around the world. And it's getting there in terms of the availability as a result. But longer term, we need to keep pushing on that, because we need to make sure that there isn't this pinch point in the system where we're now fundamentally depending upon a resource which its generation is inefficient and centralized in an instant fashion. Now, when we go beyond that then, from a diagnostic side, a lot of the concern is all, how do we create something that's going to work better at informing the final diagnosis that goes to a patient? So we have doctors and other care professionals in the loop, but relying purely on their historical expertise, of course, is not great. But you also don't want somebody basically to rely on WebMD or something to try and figure out what's going on. So the thought is, how do you make a system that can efficiently interact between a pool of professionals who are, intimately aware and working with the patient, all the way through to the world of past experience that we've seen for every case that's ever happened. And the tricky thing in that is really that we want to make sure that we are constantly feeding that stream of additional data. So there's two sides to it. I'll touch on one here and then another in just a moment. But the first side of it is that systems need to be constantly up. One of the biggest problems, if you are ever trying to sort of schedule an MRI or something like that, is just getting access to a machine at a critical time is really hard, because there are only so many of these big investments, and if you want to find time on that, then you might have to wait. So we want to make sure that we don't have any downtime, making it even harder. So just like we want to make sure that we don't have jet engines that are down for any system, we have to have reactive inventory and reactive readiness for repair immediately for any healthcare investment that we have. So we have a number of activities on basically making reactive digital twins. So what this means is that the digital twin is just a digital copy, digital version of that physical asset. It's run through the same sorts of stressors. We want to have a constant Pareto frontier of what we think are the most likely possible ways it can break and the consequential inventory that we should have for it. But going a step further than what we do for aircraft or other things which come to a central location for service, we need to actually have those parts out in vans that can get to where they need to get to. So they're literally already out there with the parts in motion to where they need to go, because the MRI doesn't come to you. So that's a big part of what we're working on right now, to try and make sure that we have minimal downtime for critical imaging. Then the next side of this is all about, okay, well, we want to make sure we have this constant flow of data. We have to make sure that we have privacy in that. So it has to be passed along in some way that is truly uninvertible. So when you think about privacy preserving AI, what it really hinges on is this idea that you can capture critical pieces of knowledge out of a stream of raw information, such that updates can be made to some model that is explanatory of not just that individual patient, but a number of patients. You need to be able to do it so that nobody can then come back and actually recreate a specific scan or tag it to a specific person. And so the challenge is, how do you learn a good means of a probabilistically uninvertible system? And it comes, for that, you can basically just explore a wide variety of different possible encodings for it, or you can try and have a system that essentially says, I want to be able to look at that, not just so that I am constantly trying to maximize the information gain for the system itself, but I'm balancing both the information gain for the learned model and also the explicit confusion of potential patients in that. So you're saying that it is trying to have a system that is going to be using an adversarial AI learning, like in a GAN or another architecture like that, but is trying to weigh off between the maximum information gain for each new piece of raw information and the likelihood that you are now distinguishing uniquely that patient. How much is this pulling away from the rest of the population? So We're looking at different architectures for doing that right now, and looking at it for very large volumes of raw imaging for the hope that we can ultimately come up with a number of things that can more and more move point of care to the home, especially when you think about aging in place more than anything else. The goal for this is that you can have somebody who can know what's going on about themselves, who can have the healthcare professionals who are helping them know what's going on without them having to come into a doctor's office, without them having to come to a doctor's office, not just for ultimate therapy, but even for that initial diagnosis. The more that we can keep people at home, the better. But to the side of therapy, the biggest thing there is now going into novel targeted therapy. So things that are not designed for millions to billions of people, but are uniquely tailored to the specific needs of the individual as much as possible. So obviously there's been work for a while in terms of targeted pharmaceuticals and like, but we are going further in terms of things like bioelectric medicine that are instead trying to look at neural mappings for individuals in order to come up with optimal activation functions that ideally will provide the best possible response for that specific person. And at the end of the day, for that, it comes down to how do we disentangle all the things that make it hard to get the individual right. So if you throw all of the genetic information you have about that person at it, if you add in tons of information about, their phone and the wearables that they may have on them, or any kind of scanning that you may have, you've got suddenly have this problem of having way too many columns. And how do you figure out what might or might not be relevant for that, even with a significant significant population of people, becomes incredibly challenging. So again, systems that attempt to look for causal links between some of these things in order to do some means of carving down and feature engineering become incredibly, incredibly necessary. And the biggest thing there is that we have to have some degree of stratified resampling. So stratified sampling, of course, here, the idea is that when you're looking across multiple populations, you want to have the ability to preserve portions of them which have shared characteristics, whether it be they share a diagnosis, positive or negative, or they share critical factors which are going to impact the selection of different therapies. If we don't have an effective stratified system in our causal-based learning, we run the risk of learning something that can either only help a very small population, or which can help everybody only a very small amount. So we're constantly looking at how we can come up with different features for that. And at the end of the day, what we're thinking about for all of this is what's the good that we're going to be able to do? Because we can look at those vast volumes of data, we can do what we can to try and model it and make more intelligent systems to help doctors do a better job, to help make things easier to provide care to people. But if we don't have that grounding, then what are we doing it for? So when we think about what we're actually trying to accomplish, the metrics by which we judge our efficacy for research, we think back to not just the papers that we're going to publish, the code that we're going to do, but we think about the people, the lives that are touched by this. And so we're actually measuring it based upon what we see as the actual positive help for the patients around the world. And likewise, when we think about it for Vernova, the goal for it isn't necessarily just counting the number of turbines, but sure, we do that too. But it's how much of the world's energy do we make, and can we keep pushing that number better and better with regards to low carbon to actually carbon negative production around the world? Because the goal is to make sure that we all have a future to look forward to there. And likewise, when we think about it for aerospace, it's going from, yes, we have lots of advanced technology out there, to more and more that is being able to be handled by hybrid electric to fully electric flight, to be able to move people around the world to where they need to get to safely in a continuous fashion that, again, will be sustainable for the future, for us, for future generations. And that's what we're doing. So we have a lot going on with all of this. It keeps us very busy, both for continuous research, but also for rapidly growing the research center. And to that end, we have, as I said, we've got now 3 advanced research centers, each of which will be looking to focus, to grow, and to improve how much of an impact they can have across the entire world. And so I wanted to throw up there and make sure that you guys knew we are actively hiring on all fronts, but at the very least, to start with, we are very much already looking to next summer for interns. And I would love to get resumes. I'd love to talk to you guys about your interests, see if they might align with some of the missions that we have. We want to make a difference with you guys. Thank you.
Thank you so much, Paul. I want to get into your intern program and also the opportunities that you have, but let's see if we have any questions. You want to do the Q&A first?
Yeah.
So, yes, hi, a question from the room.
Thank you for your offering. And I want to ask, what professional skills do you desire your potential intern should have?
Sure.
Should he be an expert in deep learning, time analysis, or what else?
Sure.
Others.
I'm going to repeat the question just for the speaker. So I'm not sure if our guests virtually can hear us. The question was, what kind of skill sets are looking for ideal candidates with Paul? What kind of, should they have deep learning or time series knowledge? And turn it over to Paul.
Sure, absolutely. So there's the cop-out answer and then sort of the follow-on to that. The cop-out answer on that is, it doesn't matter so much, and your ability to learn is the most important, which is true, but not entirely everything. So best way to think of it is, I have zero expectation that anybody that we work with will have prior experience with GE equipment. Right? They probably have never worked with GE data relative to a turbine or a jet engine or anything else, GE patient data, anything, absolutely no expectation that you would have any exposure to that, which would probably be the most immediately relevant piece. But having some exposure to different technologies is actually your best thing. It's the variety of experience that will actually serve you best. Because the thing is, we can look at, any of the different sorts of programs that we have right now, and we can try and find something that matches sort of your niche experience and, say, let's say you've done a bunch of deep learning. Right? We have a ton of different things that use deep learning, great. But if I want to find something among the set of different possible projects for this, we don't have somebody come to the research center and we just say, oh, we're going to best fit them for a specific role, and boom, they're going to do it. No, the way that we structure it is actually, you come to the research centers, and during your time, you're going to work with people who are going to help you figure out something to work on. So almost like the idea of having a senior thesis or a master's thesis or a PhD thesis. The goal is that you spend time figuring out what is the most relevant to you. So there isn't necessarily a specific vision then of expertise, because it's going to be based on what excites you from your initial exposure at one of the ARCs and where you're coming from. So there's nothing to really tailor in terms of your experience. Just know what you've liked the most. That's actually the hardest part, maybe. Bit of introspection about hey, I took a deep learning class and I kind of hated it. That's actually really helpful because it means that we can help winnow down all from a huge set of different things. Because like I said, we've got over 1,000 full-time researchers working on things all across a wide spectrum of different applications. It's easy for us to find something where you can make an impact. So the easiest thing is to make it something that is going to at least work for you.
I'm going to take a virtual one. We're gonna ping pong back and forth if everybody's okay with that. Let's see. I'm actually going to be super fair and scroll all the way up. This is us trying to. Sure. So here's the question. I have a question about what this research agenda means for GE as a company that has suffered from poor, top management decisions despite its innovation. Oh, I'm sorry. Record, is there pressure on the new combined research centers to contribute? I'm sorry, this is the mouse.
There you go. Gotcha. What's it mean for us?
Yeah.
No, it's a good question. So the answer to that is, one, each of the new business units themselves has its own independent board. That's a refresh moment for each of the actual individual GE businesses. So a starting over, a refocusing, a dealing with the sins of the past to some degree. That reckoning is actually critical because then it means that that reinvestment strategy from each of those in terms of what they look for research is much, much more refined as opposed to trying to come up with one board that says, hey, why don't you spend about $100 million a year on aviation research at the research center? We have an aerospace specific board who have very specific things in mind about where they see markets going and the needs that they need to serve as the board of that business. And so that means more guidance, more information coming into us to help us do a better job ultimately for the customers and everybody impacted by GE technology. So it's a really good question to that degree. In terms of how we see it play out and the timeline for it, so the best way to think of it is that we actually have each of these advanced research centers reporting in at the very top levels of these new businesses. So whether that be either direct to CEO or direct to CTO for each of them, independent of the actual rest of the business itself. Now that means that there's a strong sense of independent voice that should be looking forward 5, 10, 15 more years into the future, and a strong dependence upon that information coming out of the research centers for the use by the business. So if anything, it went from, yes, we need to make sure we invest in research to, no, we have to invest in much more specific, much, much heavier amounts of research across the board. So larger investments, longer term investments, specific movement in terms of things like moving into aerospace. So, yeah, no, it is highly beneficial from that side for us. It also means that researchers are focused specific to a sector as opposed to trying to simultaneously make technology across all of them. Now, we had the benefit, and we do still have the ability to continue to work together on things that we see as cross-cutting. If there's something which is going to be relevant, there's no reason why we can't jointly pursue it. But for technologies which are fundamentally aligned to just a single business, we can double down on the investment in it. And that's
Wonderful. It's wonderful to hear that GE, being such a long-standing company, is always up for innovation. Always up for, obviously, but like even in itself and its structure, you know, and how it best serves.
Yeah, no, we made it over 125 years being one single company, and the reality of today is that the vision from 125 years ago isn't going to continue to work forever. If we're not going to change, we're going to die. So we have to change. It's important that we do it right.
That's wonderful. It's wonderful to see the willingness to. Does anybody have a,
Do you also have full-time positions open in GE Research?
Absolutely. So we have full-time positions across each of the 3 advanced research centers. And so we can we're figuring out the exact postings right now. So we had a whole bunch of postings that were sort of generically tagged GE Research. Now we're kind of pulling down some and putting back up others. So we're in the process of refreshing. So I give it another couple weeks for full-time postings to be kind of sorted out. But yes, we are indeed.
Wonderful. Oh, I think we have more questions online as well. We're going back and forth. What does the recruitment timeline look like?
Sure. Okay, so 2 different things for this. So intern and then for full-time. For internships, the best way to think about it is there's technical screening and then sort of like time spent talking with management folks to understand potential fit, best possible initialization of your work. So technical screening right up front, we don't do coding interviews because they're a waste of time. They do not correlate with efficacy of the job as a researcher, so we don't do that. We do typically have at least a couple of researchers who will sit down and talk with somebody for an hour, maybe an hour and a half over Zoom or over Teams or what have you, mostly just about what you've done. Like I said, like a lot of this isn't to see if you have very specific expertise in one area, but what are you most excited by? What's your skill level in that? can we run with that? Are there multiple areas that we should be exploring there? And then that leads into the follow-on conversation, which is usually with technical management, where we say, okay, that's great. Now, who would you be working with as a mentor? Because the goal of the internship program is to have you set up with technical mentorship from day one, so that within the first couple of weeks, you've got a refined vision for what you're doing. And then you can then take that and then go forward with, okay, I now have a research plan for something that is working on real data, experimental, work, sort of confirming that and working back and forth with this technical mentor. So it's like an hour, hour and a half, and then like another half hour to an hour, a couple of calls, most of it being entirely remote, at least for the intern pathway. That's for determining whether or not it can work, and then from the research center, it's 10 to 12 weeks typically, and we go from there. But for full-time, it's a little more in-depth, just as you can imagine, you're trying to figure out a little more. So the goal for that is initial technical screening, usually 2 one-hour panels remote, and then we go to on-site, because the on-site experience is all, we want to actually show you what it's like to be there and do the real work. That ideally, the goal of it is to try and, the metrics that we judge ourselves by are like, can you meet everybody as much as possible? Can you meet all the people within your technical discipline that you're likely to interact with on a regular basis within that day? And so it's mostly about more time to talk about what excites you. In fact, to come in and start by giving like a 30-minute talk about something you worked on, like one project, one paper, just one coherent piece of work that shows you think like a scientist and we can understand how you reason and present your ideas coherently. And once you get through that, then it's all just talking through further about, the things that excite you, the things that you've got experience in, where you might take things, possible projects that you could be working on, but then meeting everybody, because at the end of the day, that's also why people take jobs and leave jobs. It's based upon what the experience is working with other human beings. And we can do that entirely remotely, and we certainly through the worst of the pandemic we did. But the goal, if we absolutely can, is to have people there so you can meet them and actually experience what it's like to, grab lunch with these people and see if they drive you crazy. So, yeah, we target like 6 to 8 hours total experience for on-site after like a couple hours up front. A quick phone call after with technical management just to make sure everything looks good and get you set for a potential offer. Yeah, so from our perspective on this, we are working all throughout the year. Anytime works for talking with us about either of these things. So I'm mentioning the research intern thing, and we frequently have interns mostly over the summer, but we can also have interns anytime throughout the year, and we're always, always, always hiring full-time. Don't ever shy away from reaching out.
Do we have another question? Yes, wonderful.
Thank you, Paul, for the session. I have 2 questions. So first off, one of them is from the slide that you mentioned about digital AI or the things that you're currently working upon for privacy preservation.
Yeah.
So are things like edge AI computing and predictive learning, such type of technologies also being implemented and really used? And if you could share one of the use cases of some project.
Sure.
And,
yeah, absolutely.
Sorry, for the second question is on the same program that you mentioned. So since it's a moderate time frame of 10 to 12 weeks, what are the expectations of after completing, some expectation of the project, right? Would it be research focused, or in the sense, would we be emphasized to publish about some of the novelties that we come up with during the process, or will it be focused towards the product?
Yeah, absolutely. Good question. So first, we'll start with the first, and actually this little product is a good way to start. This is something which is basically like, it can basically do homemade, an EKG at home. The goal is that you can basically have multiple sensors, and you can look for potential cardiac arrhythmia by having just something that is, you're able to do this with an app on your phone and a small little gadget, right? So the intelligence in being able to do that relies on a couple of things. You don't want to have a solution for that which is fundamentally entirely cloud. Obviously, that from a privacy perspective, that's a challenge. But also from the perspective of, you don't want this technology to only be useful in places where you can depend So when you have a product like this that you want to roll out around the world, and especially into places where things like power and running water are not necessarily continuous, much less internet access, you need to have the ability to have a system that can do very much focus on edge analytics in deployed settings like this, so actually in the asset itself for feature engineering to pass information to reason on the phone, and also for computing in a low size, weight, and power format on a mobile device, a tablet, or what have you. So like in a lot of our medical settings, we may have dedicated tablets throughout a hospital. They're a little beefier and more effective than a phone, but they're still not anywhere near a modern workstation. So we need to be able to do low power, low entanglement compute. So yeah, we do a ton in that space for exploration there. To your question about what we look for in terms of what's an effective research internship and everything, we're ultimately looking for novel experiences that are directly publishable for the world. So that means you work on some interesting piece of a problem. It's not in the direct critical path for completion of something that is going to be a product necessarily. It's great if it gets there. Fantastic if it's possible for it to be. But if it doesn't, we don't want everything to fall down. And we don't want you to be an intern thinking that you are basically there to crank through things to try and get the next product. That is a miserable internship experience and has nothing to do with being a researcher at all. So the goal is, can you work on something that you can help the hypothesis and solve your hypothesis, or at least come up with some understanding of the response and put it out into the world. And so typically we do we at the very least will publish everything internally. We are always generally trying to publish things externally as well. Workshops, conferences, journals, things like that. It depends on how far it gets in terms of 12 weeks isn't a ton of time. So it depends on how far things get in terms of new results, something that is potentially truly novel for scientific publication, whether you're able to then take it and run with it after you come back to your university. So, we have non-disclosure agreements, we have mutual research agreements with a number of different places, including Columbia, and that means that folks can typically continue to work on problems. Not always we can just hand over the entirety of the data set. Sometimes it's here you can see your code that you worked on. If you make refinements, we can run them back at one of the advanced research centers for you and give you additional results. And we can play the back and forth game on that in order to get to the point where you can publish that for, use as a PhD student or what have you, So, but yeah, no, our ultimate goal is to put everything that we do out into the world. It's great if we do research and it makes it into a product and it changes lives immediately. It is just as great if we can at least advance the state of knowledge so somebody else can do good things with it. Our absolute bias is publish everything.
Wonderful to hear. Let's see, we have a question. Does GE sponsor work visas? For full-time employment, like H-1B?
We do. It is limited in some regards, so we can't just blanket say yes across the board. It's candidate by candidate. I can tell you the different advanced research centers have different amounts to which they can or can't, and a lot of that is based upon things like regulatory restrictions for things like nuclear power and military aircraft engines. Certain things which we cannot have sponsored visas to support, but other things absolutely.
Good, thank you. Any other in the room questions? Great.
I was wondering, when you mentioned causal inference in the healthcare domain, how prevalent are you using this infrastructure of modeling? And is this present a problem when you have particularly extremely high-dimensional data that, when using these self-monitoring systems, have too many features?
Sure. So we're using causal systems to inform potential diagnoses, but we're not using causal systems to actually take a human out of the loop for any of this. So I'll start with that. So you try and learn something that says what you suspect is the most likely causal explanation for the information you have in order to provide both current estimation of state and forward expectation for state under different changes. So that's as I have some sense for what I think the diagnosis is today for patients, but it's truly distributional information about that. And then I have distributional information about what I expect to see if they were then to undergo a certain therapy. Now, the goal for it is to have a system which can provide that information as efficiently as possible to human experts. Because the goal here isn't to say that you take the doctor out of the loop, it's to help the doctor with as much information up front so they can then refine that into a pin. So today, they do a lot of that as best they can based upon, improved contrast for imaging, and they see, 5 different things in your record, and they try and stitch them together, right? You have an electronic health record. They're trying to sort of integrate that information themselves. This is saying, can we go a step further and try and do as much of the advanced processing on that front, especially in areas where it's not necessarily going to change the expected diagnosis, so cut as much of the potential redundant labor and have most of their time be focused on how do you find the change points between, okay, is this one thing or another in terms of taking action. So we do have quite a lot there. For the feature engineering and how we pull out good features on this, the real answer on it is that we are constantly working to refine it. So we have initial systems that they work pretty well for certain populations. They work very well for large portions of populations, but they don't work for everybody. So they're continuously learning systems. And that goes all the way from the initial feature engineering through into the models that are being developed. So it's not just, okay, well, they're going to continue to update based upon the same features coming in across populations, but where possible, we are constantly testing new potential hypothesized features and looking for whether or not they're able to reduce or uncertainty and to disentangle potential diagnosis and therapy selections. So basically, the fact that we're constantly looking for the right answer doesn't necessarily help, but it gives you a sense that we at least we're not satisfied that we're ever going to have just a static solution for this, or even that it has simple versioning to it. It has to be a continuously mutable system because it will always be exposed to new human information, new diagnoses, new consequences. And I guess that's the biggest thing to take away from it when you think about a lot of sort of the things you learn about and the way that you learn to train up something or learn to run, inference on something is you're often thinking about doing it once for a class. You're very rarely thinking about something that's going to have to do it 10,000 times a day forever, like literally forever, at the very least for decades. And so it comes down to even the things like we are constantly tracking what is the power consumption of the training and use of each of the models that we have so that we can track it back to what is the carbon footprint of every model we put out there so that we can be working to push that down as much as possible. Because at the end of the day, we want to be doing good things. So if we're just spinning our wheels too, that's also a problem. Question?
Yes, I think we have one more online.
Sure.
This was...
Yep. Combined research centers. So we have 3 research centers on the same campus in upstate New York and Esquina. So it's, I'm trying to think of how big it is. Like a dozen acres roughly in terms of the size of the campus, with a number of different buildings today. We also have we have other GE facilities just in the area. There's another downtown Schenectady location. There are other ones up in Malta. There are a bunch of different places, but the research campus itself currently is about 20 different buildings, I want to say, on about a dozen acres, and that's going to be the home for each of the 3 advanced research centers. They're all still going to be physically located there, in part because that's where all of the talent is today, but also so that they can continue to work together. Like I said, a big part of this is if we see intersectional capabilities, we do have agreements between these companies to work on them together. So the investment that is made by our aerospace, GE Aerospace business, as well as investment made by GE Vernova, can together be used to say, look for extremely high heat tolerant materials, because they both really need that. there's no reason why they should be completely independent in their
Do we have any more in the room? Okay.
Yeah, I actually interned with Paul the summer before COVID.
There you go.
And it was a beautiful research center, and it felt like a university where a lot of people are working on technical things. I actually had a question on digital twins, because I remember when I was there, they were doing it for aerospace and all of that. But when you use it for an application like healthcare, do you use, there have been people building and operating these equipment, and they have a lot of experience. Like, does it take that expert knowledge into it, or it's more of, here is the machine-specific digital twin?
So we have all aspects of the human side of this. So from human experience in the manufacturing, so we have each individual asset when it is being manufactured. We have a digital twin of the manufacturing process. Understand the tolerances and can ensure that what is going to be made will work and work as specified. But also we know individual wall thicknesses of metals, or the specifics of the materials, like the material blocks that went into each piece of manufacturing, to track down. So I mentioned being able to immediately respond to systems that go down, right? So let's say you need to be concerned about CT tubes, right? And you want to make sure that when you see one CT tube that has failed, and you're going to go into a replacement, you now know that probably everybody else who has the same batch CT tube likely to have a similar problem in a similar time span. So being able to track that down is something that we do right up front. So we do have that, but then on the human side of the actual assembly and operation, we are trying to capture that too. So in each of our factories, we have continuous observation, and we have AR/VR systems for helping to do training of systems so that people aren't learning from ground up. Actually, not something that we were very far along with when you were interning, but we're getting there in terms of, so if part of this was driven by the COVID experience, it's like, if you need to have fewer people operating much farther apart, and you have a limited pool of people who have deep expertise, suddenly you need to have factories that have information that is capturing what is the good way to do things and feeding that to help people learn to do it right. So we do have a lot more of that enabled. But then the actual operation, so where possible, we try and capture operator information and drive best practices with it. There are areas in the healthcare domain where that goes beyond the realm of things GE can do and things that other folks are contractually handling. And so we know that we have to be like, okay, we can give you information about how we think you should be picking settings for maximum contrast with the specific agent. Contrast agent, or the specific way that you're running this. And we'll even give you a calibration of it. Look, this is what we think you should do. But we can't then say, okay, we're going to lock those settings in and do it, because the actual decision to go ahead with a specific set of those is something that goes into the realm of, actual health practitioner expertise too. So we can't say that we're going to second guess their intuition every time. We're going to try and make it as easy as possible for them. We're even going to justify our we have epistemic reasoners for this, which say, I have this initial set. These are the 15 examples that gave me this reason, and I can show you that it matches in terms of past experience. They're anonymized and everything, but that information is something that is exposed to the healthcare professional when they go to take action. But it has to be their call at the end of the day.
Like a really quick follow-up. So How does it work in practice? Do they get an email on Monday morning saying, you need to do this within the next month? Or?
So in this, it's more like point of decision-making itself. So you have a healthcare practitioner who's working with like the Edison diagnostic system. And at that point, the system, they're already interacting with that digital agent. Right. And they can say, okay, now look at this. Here are these 5 cases I've seen that look just like this. Here's exactly what happened and what my recommendation is based on. If you want to think about it, it's like having a highly trained nurse practitioner or highly trained physician's assistant, somebody who has had many more years experience that is in the same practice as you, who is trying to provide that recommendation, what they might do, but not overriding the diagnosis. So it is at that interaction point. Yeah, it's not, call that guy in next month. We think that he's going to have a problem. There are some forward-looking aspects of this, but I would say the technology is not there yet, and people are definitely not comfortable with the idea of something that says, hey, we're just calling from your doctor's office. You should probably come in and check this out. We're not there yet as a society, but maybe we'll get there. I don't know.
Thanks.
Awesome.
Yeah, no worries.
So we have one question. We'll take this last question, and then we just want to touch base on how people can connect with Paul. How are research projects created top-down or bottom-up?
Sure, both. So
Okay.
we have a bunch of investment activities which are directly driven by products and services that either already exist or roadmaps. So we have a technical roadmap that aligns with each of the business and where they need to be. Based upon that, we'll know to invest in certain things. Some of them are just explicitly customer-driven. We talk with the different airlines, and they say, we need something that's 5% better in terms of fuel consumption or 10% quieter. And those are really easy to drive at. But then beyond that, we have a number of investments where it's entirely based on blue sky reasoning. So we have a significant portion of our activity which falls under the heading of independent research and development, or IRAD. And those are things where we are attempting to look at what are the things that might be game changers that we are not currently mapping to any of the products or services going forward. Can we look at those? Can we start to invest in, do experiments in them? Maybe then we'll talk with a government agency like the Department of Energy or the National Institutes of Health, convince them that it's something they should invest in. And maybe eventually down the line, it'll make its way into something. But we want to start looking at it now. And we do have that too. So the way that we do that is we have sort of an internal system for exposing those, kind of bashing them around technically, seeing if it's something that's worth investment, and then we go from there. And in terms of what people end up working on for like research internships, it can be anywhere in that spectrum too. So you might be working on something that is tied to something we know is going to be real in 3 weeks to 5 months. And then there are things where it's like, well, we need to do more in quantum computing. Sure, we're going to keep exploring in that space. We don't have anything that's a quantum product on our roadmap, but we continue to invest in quantum because sometime it might be useful. So, yeah.
Wonderful. Thank you so much for everything, Paul, today, for your great talk and great discussion. And you will be attending our career fair on October 12th. So is it 12 or 14?
14th, right?
14th. Y'all know. Okay. That's just great.
Yeah, I'm planning on being here in a couple weeks.
Yes.
In the meantime, of course, like I said, feel free to shoot me an email.
Yes.
I'm glad to talk, set up time.
Yes. So someone did ask about how to get resumes to you and everything. Paul's open to receiving emails from you, so please feel free to reach out to him or reach out to us. And if you want Paul's contact information, we're happy to connect you. And thank you so much, Paul, and we hope to have you back again.